All right, let's do some methods of moments and some maximum likelihood by hand. And by hand, I really just mean with Wolfram Alpha. We just need to get the equations into a place where Wolfram Alpha knows what to do with them. So here is the PMF for a discrete random variable. And what this could model is the trial on which the very first success occurs if we're dealing with a sequence of Bernoulli trials. So maybe we've sat down and we're buying scratch-off ticket after scratch-off ticket. X here could be the ticket number on which we win our very first prize. So it's like the geometric distribution, but instead of counting up the number of failures, it's actually letting us know the trial on which that first success occurs. And so our possible values of x will be 1, 2, 3, etc., etc. So here's the formula for our PMF. And what I would like to do is use data to figure out what the best estimate of this unknown parameter p is, the probability of each trial resulting in a success. So in this case, we're imagining that, say, everyone in BAS 471 is going off to their own gas station and buying ticket after ticket after ticket until they finally win a prize, and then they stop. And at the end of the day, they all report back to us, and we have a big collection of X's. We have a random sample from this probability distribution. Some people might have won on the very first ticket, so their little X's are 1. Some people might have taken 15, 20 tickets to win. Their little X's would be relatively large. So to get started, I'm going to write down our fundamental assumption about the data that we're working with. So what I'm going to write is that capital Xi here, and little I is just the subscript representing 1, the first observation, 2, the second observation, etc. The twiddle means that it has a probability distribution, and we're assuming that we have this probability distribution formula as up here. The IID is really the most important part. That first I stands for independent, meaning that all of the values of the little x's are unrelated to one another. The second I and the D stand for identically distributed, meaning all of the data values that I'm collecting come from this common distribution. We just don't know what little p is. And all of the values we've recorded are independent of one another. So let's talk about our two methods of estimating p from the data. Let's start out with the methods of moments estimator. So the methods of moments estimator says, well, we can measure a sample average, x bar, and we can find out what the average of the PMF is. There's a formula for the PMF. Whenever we want the average, that's just the sum over all the possible values of the little x's we might see times their probability. X times their probability here. So, Wolfram Alpha, what does the expected value work out to be in this case? Well, we can ask for the sum of x times, and then inputting our formula, p times 1 minus p raised to the x minus 1. It might be helpful to see both of these things at once. So that's our formula for the expected value. Now, I usually like ensuring that I haven't made any typos by ensuring that this sums to 1. And so let's have Wolfram Alpha plug in the values of x of 1, 2, 3, 4, all the way up to infinity. And indeed, it's a valid PMF. Those probabilities sum to 1. Once I've got that, getting the expected value is as simple as just taking that formula and pre-multiplying it by x. So we're going to end up getting a formula for that expected value. And what we find is that the expected value is 1 over p. Makes sense. If each trial has a 10% chance of success, it would take 10 trials for that first success to occur on average. And so the methods of moments estimator says that, okay, well, let's take our sample average, let's take the average from the PMF that we're working with, and let's set those equal to each other. So here's the average from the PMF. Here is my sample average that I'll eventually measure. So this is averaging all the x's that all of y'all reported back to us at the end of the day, getting those scratch-off wins. And to find the methods of moments estimator, I just need to solve for p in this case. So easy enough, I can just take the reciprocal of both sides of the equation. And to represent that this is an estimate, I'm going to put a little hat over it. I'm going to put a little methods of moments here. So my methods of moments estimator says, all right, well, if you want to use data to come up with a good guess for what the probability that any particular trial is a success, this unknown parameter p is, Just measure the sample average you've collected and take the reciprocal. All right, not so bad. What about the maximum likelihood method? Well, this approaches the problem in a slightly different manner. It says, all right, here's the probability distribution that we're working with. Let's choose the value of p so that this probability model has the highest chance of producing the data that we've collected. Now, we're going to represent the data values that we've collected not as 1, 15, 8, etc. We're going to leave it as x1, x2, x3 to see if we can develop a simple rule for what we need to do with the data in order to come up with the maximum likelihood estimate for what p is. So a lot of p's flying around. This is a capital P kind of right here. Let me differentiate that just for reference. Big P is our notation for the PMF. Little p is this probability of success, a parameter. And so how do we go about doing this? Well, maximum likelihood estimation says start out by using the probability model to form an equation that tells you the probability of observing your data. So I want to know what's the probability of observing my data. Now, I'm going to leave them as placeholders. So in other words, what's the probability that the very first data value that's collected, maybe that's you report back with a little x1. And the second data value we've collected, maybe that's your friend in this class, x2 being equal to little x2. And the third person that reports back measures the value they did, and ... all the way down to the very last data that we've collected. So I need to figure out, well, what is the probability of observing this combination? What's the probability that the first person is going to report back a 3, the second person is going to report back an 8, the third a 10, etc. And that's why this independence assumption is so critical, that first I standing for independent, meaning that all the values of the x's have nothing to do with each other. So what that tells us is that, okay, when I want to know the product of a combination of independent events, that works out to be just the product of the individual events' probabilities. And so when I do this, I can just write out the probabilities of each one of these individual observations. I'm going to be a little bit lazy and have that be the last one in the sequence, xn. And this I have a formula for. This is my formula for the PMF. I just need to plug in instead of little x, and x1 and x2, x3, etc. So I'm going to take this and say, well, probability of getting a little x1 is p times 1 minus p raised to the x1 minus 1 times p times 1 minus p raised to the x2 minus 1 times p times 1 minus p to the x3 minus 1. And we're kind of getting into that methodical rhythm. Saying that out loud is probably kind of like a lullaby. You could probably get a little kid to fall asleep if you just kind of repeated that a whole bunch. But here's the equation for our likelihood. This is the probability. If we knew what the value of p was, the probability of observing our particular combination of x1, x2, x3, etc. So we want to use Wolfram alpha to figure out, well, what value of p yields a maximum? But Wolfram alpha can't deal with this infinite product here. We need to help it out. We need to combine some terms. So since each one of these terms in the product have a common value of p, let's just group them all together. So that's going to be a p times p times p, a lot of p's, all multiplied by each other. There's going to be n copies of those, in fact. And then what I have is a 1 minus p raised to the x1 minus 1. Another 1 minus p raised to the x2 minus 1. And so I'm going to use my rules of exponents. What I notice is that each term in this product has a common base, a 1 minus p, and they're being raised to different powers. And so my rule for exponents is that when I'm in the situation, a common base raised to some set of exponents, and everything's being multiplied by each other, I'm going to take that common base, 1 minus p in this case, and then raise that to the sum of all the exponents. So this will be an x1 minus 1 plus an x2 minus 1 plus an x3 minus 1, ... all the way down to xn minus 1, that last data value that we've collected. All right, now I can further combine terms to help out with the computation. So let's see where this takes us. If I multiply p by itself n times, well, that's going to be equal to p raised up to the nth power. And if I look at all the exponents, that 1 minus p is being raised to, well, I have a minus 1, another minus 1, another minus 1. Essentially, I have n copies of that minus 1. Those are all going to add up together to give a minus n. And then I have an x1 plus an x2 plus an x3, the sum of all the x's. Why don't I use the mathematician's favorite shorthand and write that as summation notation from I equal 1 to n of xi. So things are getting a little bit simpler. How would we write the sum of all the x's into Wolfram alpha? Well, we can't. We know we're going to measure some certain value, some number for that once we do get the data. So let's use a trick that I like, and that is just replacing hard to work with symbols like the sum of all the x's just with a letter, just so we can get into Wolfram alpha. So I'm going to say, let's just let the letter s equal to the sum of all the x's. S short for sum here. So we're going to have a p raised to the nth power times a 1 minus p to the minus n plus s. So after all that work, what we find is that after we've collected a set of data, a little x1, a little x2, a little x3, all the way up to the little xn, the probability of observing that particular combination of values is p raised to the nth power, whatever p is, times 1 minus p to the minus n plus s, the sum of all of my data values. So I want to know, well, what value of p makes this probability, makes this likelihood as big as it can possibly get? So Wolfram alpha can help us out with this. We want to maximize this function. And when we maximize a function, what we'd like to do is essentially figure out, well, where is the slope of that function going to be equal to 0? So as I vary p down from 0 to 1, schematically, it's going to look something like this. It's going to rise up to a peak, and then it's going to fall down. And at this peak, if I look at the slope of a tangent line to the point on the curve, right at that peak, that slope is equal to 0. It's parallel to the x-axis. Now, with a slope being equal to 0, that allows me to figure out where that maximum is, because the equation for the slope of this curve right here is just the derivative of the function that I've plotted. So I need to ask Wolfram alpha, okay, take the derivative of this guy, figure out what the slope is as I'm varying p between 0 and 1, and then figure out where that slope is equal to 0. So how do we do this in Wolfram alpha? Well, we'll head on over. I'll move this around just a little bit. And what we're going to ask Wolfram alpha to do is to take the derivative of p to the n times 1 minus p raised to the minus n plus s. And because there's quite a few letters, Wolfram alpha needs to know, okay, well, what's changing in this expression? What am I maximizing this with regards to? And with regards to p here, so I'll add a WRT with respect to, or with regards to p. So Wolfram alpha will work hard, and it'll come up with an equation that tells us what the slope of a tangent line to this curve is at any value of p. Now that's a pretty long equation. Doesn't look like we've made much progress. We need to figure out what value of p makes this equal to 0. Well, the nice thing is Wolfram alpha can do two things at once. If I put this inside parentheses, kind of like R, Wolfram alpha will evaluate what this is equal to. It'll essentially replace that with this equation. And what I want to do is I want to solve where this equation is equal to 0 for p. So like BAS, Wolfram alpha is able to churn out a variety of different solutions. Wolfram alpha is always way too helpful. And so we just have to hunt and pick which one makes sense. So we're trying to figure out what can we measure about the data that allows us to come up with the best guess for p. And the first, the third, and the fourth solutions have nothing to do with the data that we've measured. It's only the second one that does, so we know that this one must be correct. And what we're finding is that, okay, we have that p hat, put a little hat over just to denote that, all right, this is now our best guess for what p is according to the MLE, is equal to n over s. All right, well, I want to replace what that s was by what I originally defined it to be. So that's just n over the sum of all the x's. And if you think about it, well, this is just the reciprocal of x bar. X bar is the sum of all the x's divided by n. And so if I move this n, if I multiplied kind of both of the numerator and the denominator by 1 over n, those little n's cancel. And in the denominator, I get the sum of the x's over n, and that's my x bar. So what have I found? Well, I found that both the methods of moments and the maximum likelihood procedure say to measure the same thing about the data. If you want to come up with a good guess for what P is, take a random sample from this probability distribution, have each person in the class go and scratch off tickets till they win, report back their little x's. Take that sample average, take the reciprocal. Both the methods of moments and the maximum likelihood estimator say that that is the most sensible thing to do. All right, well, let's work on a second example here. Let's go from the discrete world, where our possible values of x's are counts, to the continuous world, where any value inside of a range is going to be fair game. All right, so for this example, we're going to use this as our PDF. So if I were to make a plot of this, it's got that standard shape in analytics where it's got a right-handed skew. And maybe I just really like this shape. I just need to know what's going to be the right value of theta to use in order to model a collection of data that I have. So what I want to do is I want to figure out, okay, well, what does the methods of moments say about the thing I can measure about the data? And what does the maximum likelihood estimator say I should be measuring about the data to best guess what this theta unknown parameter is? So let's start out with the methods of moments. And methods of moments says, sure, let's do the sensible thing, and well, you're going to measure a sample average. Let's just go ahead and figure out what the average of your PDF is, and we'll set those two equal to each other. We'll figure out what the value of theta has to be for the average of the PDF to match up with the average of the sample. So the average of a continuous random variable has a definition where we just take the area under a very special curve. We take the area under the curve x times f of x. And so we just need to ask Wolfram alpha to evaluate this. Now, whenever we see infinities, either minus infinity up to positive infinity here, we always need to make sure to replace those with what the actual values that we can observe for x. Now, x has to be bigger than 0, can go up to infinity, so I'm going to immediately replace this with a 0 going up to infinity. And I'm just going to write out what my formula for that PDF was. 1 over 5040 times theta to the 8th power, x to the 7th, e to the minus x over theta, dx. Remember that dx is just a placeholder. It's letting us know that, hey, there's two symbols here. There's an x and there's a theta. This is a function with respect to x here. It's x that's varying. Theta is a fixed constant. So, Wolfram alpha, we need your help here. Can you help us out and let us know what the expected value is? So what I'm going to do is I'm going to verify that I'm working with the valid PDF by taking the area under the entirety of the curve. And I'm going to replace theta with a t. You can leave it as a theta if you want to type the whole thing out, but I love being efficient. I love typing as few characters as I can. So wherever I see theta, I'm going to replace that with a t. Now, to make sure I'm dealing with a valid PDF, that I didn't make any typos, I need to make sure that this integrates to 1. In other words, the entire area under this curve equals 1. So I'm going to integrate over the entirety of the possible values I might see for x, which is anywhere from 0 to infinity. By definition, that's what I got right here. And this better come back 1. If it doesn't come back 1, that means I must have done some sort of typo. And what's Wolfram alpha's problem? Yeah, interpreting is integrate. Let's see what the issue is going to be. So 5040 times theta to the 8th power, making sure parentheses are matched up, times x to the 7th times e to the minus x over t from 0 to infinity and beyond. So here we go. Better integrate to 1. Drum roll. Yeah, we got it. So the total area is equal to 1. No typos or anything. So getting the expected value is as easy as pre-multiplying that function for the PDF by x and letting Wolfram Alpha figure it out. So what we find is that it's equal to 8t. Now, t is just theta, and so we find that my formula for the expected value of the PDF is 8 theta. So expected value of the PDF, average value of the PDF, average value of the sample, boom, slam them together, set them equal, solve for theta here to come up with the methods of moments estimator. So what do? Well, x bar over 8. So if I've collected a random sample from this probability distribution, I guess I should write that out to make that clear. We're always going to make this assumption. If you're in grad school, you might do something a little bit more complex, but we'll always assume we're dealing with a random sample. The methods of moments estimator says, okay, you want a good guess for theta? Well, measure that sample average, divide by 8. What does maximum likelihood have to say about it? Well, maximum likelihood says, all right, well, let's do something even more sensible. Let's choose the value of theta so that the resulting probability model has the highest chance of producing the data values you collected. And just like with the previous example, I'm not going to write out actual values for the x's that make up my sample. I'm just going to leave those as placeholders, as little x1, little x2, little x3 for the first, the second, the third observation that I've collected. So when I'm dealing with a continuous distribution, I'm essentially asking, all right, well, what is that probability of observing the first data value, the second data value, the third, basically that whole combination of data values here. And because we assume independence, well, this is a remarkably easy combination to evaluate. It's just the product of the formula for the PDF evaluated each one of the data values that I've collected. And since I'm just representing those as placeholders, I'm just going to write that as x1, x2, all the way down to xn. Okay, well, I got the formula for my PDF right up here, so I just need to transcribe. So this is 1 over 5040 times theta to the 8th, x1 to the 7th power, e to the minus x1 over theta. Just taking what I see here, replacing x by x1, x2, depending on where I'm in the series. So I'll take that same formula and write this for x2 now. So it took something really simple, making it really quite hard. But we'll find this is just the right thing that I need to do in order to get the MLE and to make Wolfram Alpha work. So x to the xn to the 7th, e to the minus xn over theta. All right, we've got it. So if we knew what the value of theta was, this long expression tells us the relative probability of observing that particular combination of data values that we've collected. So we want to know, well, what's the value of theta that makes this the biggest that it can possibly be? That's a Wolfram Alpha job. We need to figure out how to write this equation into Wolfram Alpha. We need to combine some terms again. So let's do something similar to what we did before and just group like terms together. Each one of these terms has this common factor of 1 over 5040. So let's put all those 5040s together. It's going to be n copies of them. You get the idea. Then I have this common factor of 1 over theta to the 8th in every single one of these terms. So let's go ahead and just take all those 1 over theta to the 8ths, group them together. And then I have an x1 to the 7th times an x2 to the 7th, x3 to the 7th, a whole bunch of things multiplied by each other. Each one of those things are raised to the 7th power. Now I can use my rules of powers again. So if I have a bunch of numbers, each with different bases potentially, but they're all raised to the same power and everything's multiplied by each other, what I can do is I can actually group all of those bases together in one big old product, x1, x2, x3, all the way down to xn, and raise that product to that common power. So those are dot, dot, dots. That's not a minus sign. I'll put Make that one big dot there. And then finally, what we have is e raised to a power times e raised to another power times e raised to another power. So common base for each of those terms, different exponents for each of those bases, but everything is multiplied by each other. And so our rule is, well, if I have a common base multiplied by itself and everything's just raised to a different power, I get to add all of those powers. So that'll be e to the minus x1 over theta minus x2 over theta minus all the way down the line to xn over theta. And now the fun happens. We get to start combining terms and see how we can get this into Wolfram alpha. So n copies of 1 over 5040 all multiplied by itself. That's going to become 1 over 5040 to the nth power. I have a 1 over theta to the 8th power multiplied by itself n different times. And here's another rule of powers that you might have forgotten. If I have a number like a raised to the b power, and I take that and raise it to the c power, the result is actually just multiplying those two exponents together. So here I have a 1 over theta to the 8th. That whole quantity raised to the nth power, because I have n copies of this in my product. So those exponents, that n and the 8, are going to multiply, and I'm going to get 1 over theta to the 8n. Now, I'm going to use mathematical shorthand here. Here I have all of the x values multiplied by each other, and the mathematical shorthand is to use the product symbol. The product of I equal 1 to n of xi. And that's going to be raised to the 7th power. And then I have e raised to something here. Now I'm going to take out a common factor of minus 1 over theta from each one of these terms. And then what I'm going to have left over is a minus 1 over theta times x1 plus x2 plus x3 plus x4 times the sum of all my x's. So I can almost get this into Wolfram alpha. I just need to come up with an abbreviation, a symbol, to represent this number, whatever it works out to be once I take my data, and this number, the sum of all the x's once I take my data. So why don't I go ahead and let s be equal to the sum of all my x's, and why don't I let p be equal to the product of all of my x's, and I'm going to raise that to the 7th power as well. I could do it without raising it to the 7th, but I want to just do it in one fell swoop. And so what my equation is for my likelihood works out to be 1 over 5040 to the nth power, theta to the 8n power, times p times e to the minus s over theta. That's not so bad. That's something I can write into Wolfram alpha, so I'm one step away from figuring out the maximum likelihood estimate. What I need to measure from the data to come up with an estimator that has the highest chance of producing the data that I've collected once I plug that into the probability model. So let's ask Wolfram alpha to help us out. So what I need to do is figure out, okay, if I take this derivative, set it equal to 0, what value of theta emerges? So let's take the derivative of 1 over 5040 to the n times 1 over t raised to the 8 times n power, abbreviating theta by t, times p times e raised to the minus s over theta. So we'll confirm Wolfram alpha can do this. I didn't make any typos. We get an equation. It's not pretty looking. But what I want to do is really just figure out, well, what value of theta here is going to set this equal to 0. That's going to be where this likelihood is peaking. So I'm going to wrap that inside parentheses and then say, okay, we'll solve that expression, solve this guy equal to 0 for theta. And in fact, I omitted something from the last equation that just shows you how smart Wolfram alpha is. Wolfram alpha knew, once I typed out this massive expression, that I wanted to take the derivative with respect to theta. There's a lot of unspecified values here. There's an n, there's a t, there's a p, there's an s. Wolfram alpha was so smart that it knew, hey, this guy probably wants to take the derivative with respect to theta. I'll help him out there. Now, sometimes Wolfram alpha isn't that good of a guess, so I'll say with respect to theta here. But we want to figure out where this peaks. So Wolfram Alpha, very helpful, giving us 3 solutions. We need to figure out, okay, well, which solution tells us what we can measure from the data to get our estimate. The first doesn't make any sense. The last doesn't make any sense. T theta here in this case. I'll put a little hat over it. We find that theta is equal to S over 8n. And S, if you remember, was just our abbreviation for the sum of all the x's. And well, why don't I write this as 1/8 times the sum of the x's over n. And this is our old friend, just x bar. So how about that? Both the methods of moments estimator and the maximum likelihood estimator say to do the same thing with your data. If you want to know what a really good guess is for theta here, based on matching moments or picking the value of theta that gives the resulting probability model the highest chance of producing your data, well, what you want to do with your data is to get that sample average and divide it by 8. Both methods agree. And so that's nice. It's nice when both agree, but they don't always. So let's work on another example, and let's see if we can maintain this agreement. Boy, I got a lot of examples here. You can tell I like doing this. I could do this all day long here. So here's kind of a cool distribution. X is going to be between 0 and 1. So like the beta distribution, we've talked about the beta distribution being very flexible for values of x between 0 and 1. And so this gives what we refer to as a power law behavior. Now, if theta is really big, what ends up happening is that this kind of grows like this. If theta is small, bigger than 0, but say less than 1, it's going to go like this. It's going to undergo some sort of power decay here, power law decay. So if I've collected a random sample, I went out and measured n different values of the x's. They're all coming from this distribution. They're all independent. Well, what should I do with my data to best estimate theta here? Let's do the methods of moments. Methods of moments says, well, you're going to measure a sample average with your data. Let's figure out what the average of the PDF is and just set those equal to each other. Let's figure out what the value of theta is in order to make those two averages match up. So let's get this right. How do we get the average value? Well, the average value is the integral over everywhere of x times our formula for the PDF. But we always immediately change the minus infinity to the actual upper and lower limits that x is allowed to be. So between 0 and 1 of x times theta to the x raised to the theta minus 1. So Wolfram Alpha help us out. So my trick is always to start out by just integrating that PDF. I'm going to abbreviate theta with t and making sure that the integral is equal to 1. That's how I know that I'm dealing with a valid PDF, so cross fingers, better evaluate to 1, and we find that that's the case. Great. So valid PDF, that means getting the expected value. The average is trivial, just pre-multiply your formula by x. And what we find is that the expected value of this distribution is t over t plus 1, so theta over theta plus 1. All right, well, we have the average for the PDF here. We have the average for the data values we've collected. Let's figure out what value of theta we have to have in order for these two things to match up. So let me get that. All right, so we need to figure out what value of theta is going to make the average value of the PDF equal to the average value that we measure from the sample. So we just need to solve this equation for theta. Now, this one isn't too bad just by doing the algebra, but let's Wolfram Alpha it. So Wolfram Alpha is great at solving algebra. We want to solve the equation t over t plus 1 equals, we'll call it capital X, for theta. So Wolfram Alpha will work its thing. And it says, all right, we'll take your theta hat to be equal to minus x bar over x bar minus 1. Now, you might ask yourself, is that right? Because didn't I at the very beginning of this say that theta is equal to 0? How is there a negative sign here? Well, remember that all of the x's are going to be between 0 and 1. So x bar is going to be between 0 and 1 as well. So x bar minus 1 is actually going to be negative, and that'll wipe out the negative sign out in front. In fact, if I just write this as x bar over 1 minus x bar, that kind of takes care of that awkwardness. So method to moment says, okay, you've taken a random sample. Well, to use that random sample to estimate theta here, just take the sample average and divide by 1 minus the sample average. Okay, so what does the maximum likelihood estimator have to say about it? Well, let's see what the MLE is for theta. What should we measure according to the MLE to best estimate what theta is? So we start out by writing out the likelihood. That's the probability of observing our particular set of data values. Once again, just leaving them as placeholders, little x1, the first data value, little x2, the second data value, etc. And because we've assumed independence, the probability of this combination is easily evaluated as just the product of the PDFs evaluated each one of the sample values. So we're going to have a theta times x1 to the theta minus 1 times a theta x2 theta minus 1 all the way down the line theta xn theta minus 1. So we want to know what's the value of theta that's going to make this as big as it can possibly be. Wolfram alpha is going to help us out, but we need to figure out how do we get this into Wolfram alpha. We need to simplify this expression. So once again, I see that every term has a common value of theta. Let's just take all of those and group them together. So we have n copies of theta being all multiplied by itself. And then I see I have a whole bunch of things all raised up to the theta minus 1 power. So different bases all raised to the same power. The rules of powers, the rules of exponents say we'll take the product of all those bases and raise it to that common power. All right, well, we're almost there. If we have theta multiplied by itself n times, that's just theta to the nth power. And we can abbreviate the product of all the x's as the product from I equal 1 to n of xi using product notation raised to the theta minus 1 power. So that looks like something that we can put into Wolfram alpha as long as we abbreviate this product of all the x's by something. So let's go ahead and say P, short for product, is the product of all of the x's that I'll eventually measure in my sample. So once I do that, this is not too bad of an expression to put into Wolfram alpha to figure out where the maximum value is. So let's get some help. So what we want to do is we want to take the derivative of theta to the n times p raised to the theta minus 1 power with respect to theta. We want to know what value of theta is going to make this as big as possible. We know it's bigger than 0, so as theta varies, how does this likelihood vary? All right, so there's our derivative, hard equation to work with, but we don't need that equation directly because if we just want to figure out where that derivative is equals to 0, we'll just wrap that inside parentheses and say, okay, Wolfram alpha, solve this equation, whatever pops out of it. Solve the derivative equal to 0 for theta. What value of theta makes this expression equal to 0? And we'll find that theta hat in this case, one of these three things. Which one can we actually use the data to measure? Well, this very last one. This is a minus n over the log of p. Okay, well, what is the expression for p here? That's minus n over the log of the product of all the x's that we've measured in the sample. Now, here's one of my favorite things about logs. If I were to look at this, I would say that, okay, if I were to just expand this out, kind of undo that abbreviation, this would be the log of x1 times x2 all the way down to xn. And one thing I know about the log of a product is that's the sum of the logs of the components of that product. So the log of x1, x2, all these multiplied by each other, would be the log of x1 plus the log of x2 all the way down the line. Now, why don't I re-abbreviate this? And you might think, we're really wasting time here, but this is what mathematicians love to do. This is the sum of the log xi's. And this kind of looks like an average. Whenever we sum up a whole bunch of things and divide by how many there are, that's an average. So this is like saying it's minus 1 over the average value of the logged values in the sample. So that's taking it a bit further than what we really need to be. This is a perfectly adequate expression for what the MLE is, but I feel like we added a little bit of understanding by pursuing what this simplifies to. So the method to moments estimator says, okay, what can we measure from the data to come up with a good guess for this unknown parameter? Well, take the sample average, and then take that sample average divided by 1 minus that average. Maximum likelihood says, well, okay, well, here's something else you could do. Look at the logarithms of all of your data values, treat those as your sample values, and do the reciprocal of the average of the logged values, and then flip the sign. So minus 1 over the average of the logs. Okay. So finally, an example where we have a little bit of disagreement, it's not a bad thing, between these two methods. They're both unbiased, as we'll talk about in Unit 10, or the last part of Unit 9. The maximum likelihood estimator is a little bit better than the method to moments, so if we had to choose one, in a large sample, we would choose this one right here, but that's a topic for another time. So let's do one more example. Let's do a fun example. That was some thunder. So here's an example of a location-shifted exponential distribution. So we've talked about the exponential distribution. It's memoryless. Its shape looks like this, just decays off exponentially. Larger values are progressively less likely to be seen. And let's imagine that there's a minimum possible value that we can see. So exponential distributions are very often used to model, say, waiting times. Let's imagine that there's just no way you could ever wait less than 5 minutes for something to occur. So if that's the case, the time beyond 5 minutes might be exponentially distributed, but we have this hard-coded lower value of beta here. So let's imagine that we've collected a whole bunch of values from this distribution. We're dealing with a IID sample. All my x's are independent. They're all coming from this distribution. I just don't know what that lower bound is. What is this minimum waiting time? How can I use my data to estimate this? All right, well, let's do the MLE. This one's kind of fun. If I were to write out the likelihood, I'm going to skip a step. That's just the product of my formulas for the PDFs, plugging in little x1, little x2, all the way down the line. And so this would become e to the minus x1 minus beta, e to the minus x2 minus beta, all the way down the line, to e to the minus xn minus beta. Okay, well, common base, e, raised to some powers here. But everything's multiplied by each other, so my rules of exponents say, well, I'll take that common base, and all the logs are going to add. Now, what I'm going to do is I'm going to expand this minus sign inside each one of these. The minus beta becomes a positive beta. So I'd have a minus x1 plus beta, minus x2 plus beta, minus x3 plus beta, minus dot dot dot, minus xn plus beta. And let me group some terms. So I have beta added to itself n times. That will be an n times beta. And then I have a minus the sum of all the x's. So why don't I write that as just minus the sum of all the x's here. So that's not too bad. Why don't we abbreviate the sum of all the x's by s here, kind of our favorite abbreviation, and say, hey, Wolfram alpha, where does this peak? What's the value of beta that I should take that makes this likelihood as big as it can possibly be? All right, well, let's solve for the derivative of this guy. So e to the n times b for beta minus s with respect to b for b. So take the derivative of that expression with respect to beta, figure out what value of beta makes that equal to 0. And here we have the oddly bizarre result where Wolfram Alpha just says false. Kind of like Dwight Schrute in The Office, if you've seen that. So what went wrong here? Wolfram Alpha failed us. It says, hey, I can't solve this equation. That's too hard for me. Well, what went wrong was that this is one of the examples where math is actually going to fail us here. Why is it going to fail us? Well, we have this interplay between the possible values of x that we might see and this value of the unknown parameter. I've mentioned in class that every time we see a scenario that looks like this, where that unknown parameter is tied into the possible values of the x's, if we try to Wolfram Alpha it, if we try to solve for the MLEs numerically, if we try to math it out, it's going to fail us. So why does that actually happen? Well, let's talk about where the likelihood actually is. Let's use logic instead of math, well, a little bit of math, to figure out what the MLE needs to be. All right, so I'm going to work with our expression for the likelihood right here. And S is something that I've measured from the data. It's the sum of all the data values. And so my likelihood is just e raised to the sample size times beta minus S. Now, I know that procedurally, at least, the reason that I was taking that derivative, setting it equal to 0, was to figure out where the likelihood peaked. I want to know where the maximum value is. Well, this isn't too complicated of an expression. I can ask myself, well, what values of beta are going to be associated with big likelihoods? Is it small values of beta, big values of beta, something in between? What's the story here? Well, if I take beta to be a bigger and bigger and bigger and bigger number, well, what happens is that this exponent also gets bigger and bigger and bigger. So if I were to plot that likelihood with respect to beta here, we essentially got it going up and up and up and up. In fact, there's no limit to how big the likelihood can get. If I plugged in beta equal to infinity, I'd get an infinite likelihood out. And that sounds appealing because I want to maximize it. But I need to take a step back and think about, does that make sense? Can I take beta to be as large as I possibly can? And to help put this in the context, let's imagine that our random sample were these 3 values. Just kind of picking some values here. 4 values, not too many. Let's imagine my random sample looked like this. I'm asking the question, can I take beta to be arbitrarily big? Can I make this likelihood go off to infinity? I want to maximize it after all. And the answer is no, because of this interplay. What I have is that whatever the value of beta is, all my x's have to be at least that big. So if I look at my data, would I be able to take a value of beta equal to 1? I'll write that here as a reminder. Could I take beta equal to 1? Well, yes, all of my data values are at least 1. Could I take it equal to 1.1? Sure, all my data values are still at least 1.1 here. Could I take a beta equal to 5? That's a little bit bigger, maximizing the likelihood is what I want to do. Well, no, because if beta was equal to 5, it would have been impossible with this probability to model to see this 3.2. It would have been impossible to observe that 1.2 as well. So choosing a value of 5 yields the probability model being fundamentally incompatible with the data that I've collected. So with that in mind and with that line of reasoning, what's going to be the largest value of beta that I'm essentially allowed to take once I've observed a random sample? Well, if you thought it out, the minimum value of x is kind of my constraint right here. If I took beta to be any bigger than 1.2, I would have made it impossible to observe that 1.2. So the biggest that beta can get is this 1.2. So in general, well, 1.2, that's the smallest value of my random sample. Beta hat is going to be equal to the minimum of all the values that I observed. So if I'm dealing with an exponential distribution, but with a minimum wait time, this location shifted exponential, fairly easy rule to know what to do with the data once you've collected it to come up with the maximum likelihood estimate, the value of beta that gives the resulting model the highest chance of producing the data that you collected. And the simple rule is, well, look at the smallest value. That's going to be your MLE estimate for beta. And it kind of makes sense. You know, if beta is this minimum waiting time, it kind of makes sense to just look at all the times you've collected and take your smallest. That kind of gets you closest to what that beta is. And so there is that nice intuitive connection so that we're not all completely lost in the math here. But there we go, 4 examples of maximum likelihood estimation and methods of moments. A lot of math. The nice thing is, R is actually going to be able to help us out and kind of make us not have to go through all of these steps, and we'll be able to solve, numerically at least, for the MLE estimates based on a random sample we've collected on a case-by-case basis. So we'll lose the ability to have these little simple rules like, oh, we need x bar over 1 minus x bar, or the minimum value of the x's, or the reciprocal of the logs of the x's after flipping the sign. So we'll lose that little bit of insight, but we'll always be able to come up with an answer. So stay tuned.